Hello, welcome to Advanced Composites. Today is the second day of the ongoing week, and yesterday we just finished developing two equilibrium equations. The first one was related to force equilibrium in the x direction, and the next one was force equilibrium in the y direction. Today we will extend that discussion because ultimately we have to satisfy 6 different equilibrium conditions. So, the third equilibrium condition is that sum of forces in the z direction should be equal to 0. Now, yesterday when we started discussing and we were talking about force equilibrium in x and y directions, we had only listed forces in the x and y directions because those are the only forces we wanted. We could have put other forces also in the z direction also, but it would have made this picture much more complex. So, to avoid complexity and this picture meets our needs, we did not put any forces in the z direction. So, today we will start seeing what kind of forces are there on the plate. So, if you look at the plate and typically, for instance, consider this is a piece of wood, it could be considered as a composite, and if I put some load on it, there is a vertical force which is acting on this plate. Okay. There is a vertical force which is acting on a plate, and in a lot of cases plates are required to handle vertical loads, because for instance this roof or whatever, this table, these are plates and they experience external loads in the z direction. So, there is load in the z direction, and this load could be uniform, it could be a point load or it could be a distributed load. So, we will say that there is a load distributed in the plate in the vertical direction, and it is q newtons per square meter. Okay, this is the vertical load. So, this is one load, but for equilibrium we have to see all the loads which are there on the plate. Okay. So, the other thing is that when we were developing our equations to connect mid-plane strains, and when we were developing these equations, epsilon is equal to epsilon naught minus, or actually it is z times mid-plane curvatures, we had made two important assumptions. What were those assumptions? The first assumption was that if I bend the plate, there was a normality assumption, right. So, whatever, so if I am bending a plate and suppose this edge is normal to this line and this line, and when I bend the plate, then this edge remains normal after it is bent. Okay. So, we had a normality assumption. And a consequence of this normality assumption was that we said that gamma zx is equal to gamma zy equals 0. Okay. So, this was the normality assumption, and because of this we also said that because shear stress zx, shear strain zx and shear strain zy is 0, and because at each layer the fibers are running parallel to the plane, we also said that tau zx is equal to tau zy is equal to 0. Okay. So, this is tau zx is equal to tau zy is equal to 0, and the second one was that in extensibility assumption, and what does that mean? That if I am bending the plate and I am stretching it, the dimension of the plate in the z direction, it is not changing, it is not changing. So, we had said that epsilon zz or epsilon z is 0. Okay, epsilon z is equal to 0. Now, these assumptions are belong to a theory of plates called Kirchhoff plate theory. Kirchhoff plate theory, right. So, the first assumption is related to normality and the second one is related to inextensibility. Now, consider this: if there is a plate and suppose it is seeing some external transverse load qxy, and I am actually just drawing the 3-dimensional because it has some thickness. I am not drawing just the midplane, but also the thickness. If what is tau, so this is my x axis, this is my y axis, and this is the z axis. Based on the sign convention, what is tau zx? Tau zx will act in this direction. This is tau zx. And what is tau zy? This will be tau zy. And likewise, we will also have shear stresses tau zx on the other side and tau zy on. So, we will have tau zy on this plane and tau zx on this plane, right, based on our sign convention. But based on our assumptions, all these stresses are 0, all these stresses are 0, because we have assumed gamma zx is equal to 0, gamma zy is equal to 0. Now, if these stresses are 0, then there is nothing to resist q, there is nothing to resist q. If tau zx is equal to tau zy is equal to 0, there is nothing to oppose qxy, right, because there is no other external force on the system, there is no other external force. I am just cutting a piece of this plate, and on this surface the only force which can resist has to be created because of tau zx. If tau zx is 0 and tau zy is 0, nothing will oppose this qxy. Okay. So, what does that mean? Then the condition for equilibrium will be q times dx times dy is equal to 0, which means that q should be 0. Q should be 0, but we know that plates, when we put loads on them, we are actually applying q's, and q is not 0 in reality, because most of these plates, they are subjected to external transverse loads and they are able to bear those loads. All that this discussion means is that our assumptions related to gamma zx and gamma zy, they are not necessarily true and they are not accurate, because they contradict reality. So, Kirchhoff plates normality assumption it is not, it contradicts reality. It contradicts reality. Okay. So, this is something important to understand. So, we cannot say, and because of this we cannot say that tau zx is 0, it cannot be 0 in general, and similarly tau zy, it cannot be 0 in reality. So, there is a defect in Kirchhoff's plate theory, okay, and we have identified this defect and now we will correct this defect. So, we say that, well, these shears are not necessarily 0, okay, and if I integrate this shear along the thickness of the plate, So, if the plate thickness is minus h by 2 to h by 2, then I get, just as I get a force resultant in x and force resultant in y direction, similarly I get a force resultant in z direction, and because it is an integral of tau zx, I call it qx. And what is the direction of qx? Direction of qx is in z direction, okay, because tau zx is acting in the vertical direction, okay, and we call it qx because it is acting on the x plane, it is acting on this surface. So, that is why we call it x, but its direction is in the z direction, understood. Similarly, if tau zy is not 0, then if I integrate it, then I call it qy, and the direction of qy is in z direction also, okay. So, note these are not forces, qx is not force, qy is not force, it is a, these are force resultants. And they are due to out of plane shear, out of plane shear stress, they are due to out of plane shear stress. So, now that we have developed a theory for qx and qy, we will again draw the midplane of the plate with all the vertical forces or force resultants acting on it, okay. So, let us look at this plate. So, again we will draw a midplane. So, this is the midplane, my x axis is here, this is the y axis, this is the z axis, okay, and this plate is seeing a vertical force which is distributed in nature. So, this is qxy, and at the midpoint, at origin, force resultants in the z direction are qx and qy. So, we are just putting force resultants in the z, we are only putting z direction related components, okay, not x and y related components, because they do not matter if we are trying to find equilibrium in the z direction. So, at origin if we have qx and qy, then on this surface, so again this is delta x and this is delta y, then here I have qx plus del qx over del x times delta x over 2, and on this side this is my other qx. So, this is qx minus del qx over del x times delta x over 2 on the other surface by Taylor series expansion, and on this plane I have qy plus del qy over del y times delta y over 2, and on the other plane I have qy minus del qy over del y times delta y over 2, okay. Is this clear?
Direction will be negative.
Direction will be negative because whenever we have shears, if you have a shear here, then on the other surface shear is always like that, right. So, direction will be negative, okay. So, if we sum up all the forces in the z direction, sigma of Fz is equal to 0, then what do we get? We get Qx plus del Qx over del x times delta x over 2 times delta y, right, minus Qx minus del Qx divided by del x times delta x over 2 times del y plus, we will write the components due to y, Qy plus del Qy over del y times delta y over 2 times del x delta x minus Qy minus del Qy over del x, oh I am sorry, del y times delta y over 2 times del x. So, these are the forces due to Q's. These are the forces due to Q's, right. So, these are the forces due to these 4 Q's, but there is a fifth force which is related to this external load Q. So, what is the force due to this? It is Q, which is a function of x and y, times the area of the plate, which is del x times del y, and all of these guys, they add up to 0. Okay. So, these terms go away. Also, this term delta x, delta y, they also go away. So, the equilibrium equation for the z direction, it becomes del Qx over del x plus del Qy over del y plus Q of xy is equal to 0. So, this is the equation for, so this tells us about force equilibrium in z direction. Z direction. So, we have developed 3 equations related to force equilibriums. First one is Fx is equal to 0, second one is Fy equals 0, and the third one is Fz is equal to 0. And as I said earlier, if there is a particle which is subjected to external forces, and if it is a point object, then the only equations we have to worry about is force equilibrium equations. But since this small element of plate is not just a point object, but it has a finite non-zero size, so we also have to worry about moment equilibrium equations. So, starting next week, or not next week, starting tomorrow, we will start looking at these moment equilibrium equations, and we will also develop moment equilibrium equations related to sum of moments in x direction, y direction and z direction is 0. So, that concludes our discussion for today. We will look forward to seeing you tomorrow once again in context of these moment equilibrium equations. Thank you. Bye.